Your brand new car just hit 50,000 miles and the check engine light comes on. You take it to the dealer and they tell you the engine needs a complete rebuild. This is happening more often than you think, and it is happening with brands that used to be bulletproof. Before we go deeper into this, leave a comment with your name and which city you are watching from. We love knowing where our audience comes from. In the next few minutes, you will understand exactly why modern engines are failing earlier than the ones from 20 years ago, and what specific changes in engineering are causing this. The first thing you need to know is that your new engine is not built like the one in your dad's truck. Modern engines run something called the Atkinson cycle in many cases, especially in hybrids. In a traditional Otto cycle engine, the intake valve closes right when the piston starts moving down. In an Atkinson cycle, the valve stays open longer, letting some of the air-fuel mixture escape back into the intake. This sounds like a waste, but it increases thermal efficiency by about 12%. The problem is that this creates uneven pressure distribution across the piston rings during the compression stroke. Over time, this uneven loading causes microfractures in the ring lands, the grooves where the rings sit. When a ringland cracks, compression leaks past the piston, oil burns in the combustion chamber, and you get carbon buildup that accelerates wear. This is why you see oil consumption issues in engines like the Toyota 2.5-litre, 4-cylinder, and certain Honda Earth Dreams units before they reach 60,000 miles. Next, let's talk about direct injection. Almost every new engine today injects fuel directly into the combustion chamber at pressures between 2,000 and 3,000 psi. Port injection, the old method, sprayed fuel into the intake port where it mixed with air before entering the cylinder. That fuel spray also washed the back of the intake valves, keeping them clean. Direct injection skips that step. The intake valves never get that fuel wash, so carbon from the crankcase ventilation system, which recirculates oil vapor to meet emission standards, builds up on the valve surfaces. After 30,000 or 40,000 miles, you can have carbon deposits thick enough to prevent the valves from sealing properly. When a valve does not seal, compression drops, the engine misfires, and unburned fuel washes oil off the cylinder walls. That oil loss leads to scuffing on the cylinder walls, which leads to more oil consumption, which leads to more carbon. It is a cascade. The third factor is turbocharging on smaller engines. Manufacturers are putting turbochargers on 3-cylinder and small 4-cylinder engines to replace the power of larger naturally aspirated engines. A 1.5-litre turbocharged 4-cylinder in a mid-size sedan is now doing the work that a 2.5-litre or 3.0-litre engine used to do. The turbocharger spins at up to 150,000 RPM and heats the exhaust gases to over 1,500 degrees Fahrenheit. That heat soaks into the cylinder head. The problem is that small engines have less thermal mass. A larger engine block and head can absorb and dissipate heat more effectively. In a small turbocharged engine, the head stays hotter for longer, and the oil that lubricates the turbo bearing and the valve train breaks down faster. When oil breaks down, it loses viscosity, and the turbo bearings start to wear. Turbo failure often sends metal particles through the intake system, scoring the cylinder walls. Even if the turbo does not fail completely, oil consumption goes up because the piston rings are running in oil that is already degraded. The turbo itself relies on a bearing system that floats on a thin film of oil. In older, naturally aspirated engines, bearing clearances were measured in thousandths of an inch. In a turbo bearing, the clearance is measured in tenths of thousandths. That means even a small drop in oil pressure or a delay in oil flow during cold starts can cause the bearing surface to contact the shaft. Each contact event removes a microscopic layer of the bearing material. After enough cold starts without proper warm-up, the bearing develops play, the turbo starts to wobble, and the compressor wheel hits the housing. That is when you hear the whine or whistle that means your turbo is about to fail. Now let's look at the oil itself. To meet fuel economy standards, manufacturers specify lower viscosity oils. 20 years ago, 10W30 or even 10W40 was common. Now many engines call for 0W20 or even 0W16. These oils flow easier when cold, which reduces friction and improves fuel economy by about 2%. But they also form a thinner film between metal parts at operating temperature. In a high-load situation, like climbing a hill with the air conditioning on, that film can break down momentarily, and you get metal-to-metal contact. This is called boundary lubrication failure. It happens most often at the top of the cylinder, where the piston speed is lowest and oil film is thinnest. Over time, this creates wear patterns that look like vertical scratches. Once those scratches are deep enough, the rings cannot seal, and you are back to the oil consumption problem. There is also the issue of extended oil change intervals. Manufacturers now recommend oil changes every 10,000 miles or even 15,000 miles. This is based on laboratory testing under ideal conditions. But in real-world driving, especially short trips where the engine never fully warms up, moisture and fuel dilution accumulate in the oil. That contaminated oil accelerates wear on the camshaft lobes, which are some of the highest loaded parts in the engine. A worn camshaft lobe means the valve does not open as far, which reduces airflow, which reduces power, which makes the engine work harder, which increases wear everywhere else. Another element is the timing chain. Many modern engines use a timing chain instead of a belt because chains are supposed to last the life of the engine. But to save weight and cost, the chains are narrower and the tensioners are smaller. The tensioner is a spring-loaded arm that keeps the chain tight. If oil pressure drops even slightly, the tensioner does not push hard enough and the chain starts to slap against the guides. This wears the guides, which are made of plastic, and eventually the chain skips a tooth. When that happens, the valves and pistons collide and the engine is destroyed. This is especially common in GM's 2.0-litre and 2.5-litre Ecotec engines and some Ford EcoBoost units. Variable valve timing adds another layer of complexity. Most engines now have actuators on the camshafts that change valve timing on the fly to optimize power or efficiency. These actuators are controlled by oil pressure through narrow passages in the camshaft. If the oil is dirty or the passages get clogged with carbon or sludge, the actuators stick. A stuck actuator means the valves open at the wrong time, which can cause a valve to contact the piston. Even if it does not cause contact, it creates a rough, idle, poor fuel economy and eventually a check engine light. Repairing it often means replacing the entire camshaft assembly, which can cost thousands of dollars. The oil passages that control these actuators are sometimes as narrow as 2 millimeters in diameter. They wind through the cylinder head in paths that were optimized by computer simulation to save weight and material. The problem is that these narrow passages trap particles that would have flushed through a wider passage in an older engine. A single particle of carbon or metallic debris can partially block the passage, reducing oil flow to the actuator by 30 or 40%. When that happens, the actuator response time slows down, the engine computer tries to compensate by adjusting other parameters, and you end up with valve timing that is slightly off across the entire RPM range. This reduces power and increases fuel consumption, but not enough to trigger a warning light immediately. By the time the light comes on, the problem has been damaging other components for thousands of miles. Finally, there is the human factor. Modern engines are designed with very tight tolerances to maximize efficiency. That means they are less forgiving of neglect. If you ignore an oil change, run low on coolant, or use the wrong fuel octane, the damage happens faster than it would in an older, more robust engine. A 1990s Toyota or Honda engine could survive a missed oil change or two. A 2020s engine might develop permanent damage after just one. The engineering goal was efficiency, not durability under abuse. So what can you do? First, change your oil every 5,000 miles, regardless of what the manual says, especially if you drive in stop and go traffic or make short trips. Use a high-quality synthetic oil that meets the exact specification in your owner's manual. Second, if your engine has direct injection, consider using a fuel system cleaner every 10,000 miles that is designed to clean intake valves. Some people also do a manual walnut blasting service where crushed walnut shells are blasted through the intake to remove carbon buildup. Third, let your engine warm up for at least 30 seconds before driving and avoid hard acceleration until the temperature gauge is in the normal range. Fourth, if you have a turbocharged engine, let it idle for 30 seconds before shutting it off after a highway drive. This lets the turbos slow down and cool down while oil is still circulating. And fifth, pay attention to any unusual noises, smells, or warning lights. Modern engines give you very little warning before a small problem becomes a catastrophic failure. If something seems off, get it checked immediately. So leave another comment below telling us which city you are watching from, and if you found this useful, subscribe to the channel so you do not miss our next breakdown. We will keep analyzing the engineering behind the machines you use every day.